All right, today we're jumping into a project that's pretty incredible. It's essentially a digital guardian for our satellites, and it's tackling a huge, and I mean huge, problem happening hundreds of miles above our heads. So let's explore the software that's designed to protect our vital infrastructure in the very, very crowded highways of space.
So let me just start by asking you this. What do you think happens when a satellite, this marvel of engineering that's worth millions, is on a collision course with a tiny piece of junk moving at thousands of miles per hour? Well, the answer is, it's catastrophic. And this isn't some sci-fi movie plot, it's a very real, daily risk for the thousands of satellites we all rely on.
So to really get how we can prevent that disaster, here's our roadmap. We're going to start by getting a feel for just how bad the problem is up there. Then we'll meet the digital guardian built to fix it, we'll peek under the hood at the tech, and then walk through its step-by-step playbook. We'll even see how you can run the code yourself before we wrap up by looking at what this all means for the future of orbit.
Okay, first things first, let's set the stage and look at the scale of this problem. This is section 1, the crowded skies, where we're going to dig into just how serious this orbital traffic jam has really gotten.
You know, it's so easy to think of space as this vast, empty vacuum, right? But the area right around our planet, what we call low Earth orbit, is, well, it's anything but empty. The best way to think of it is as a cosmic highway, and right now, that highway is stuck in a massive traffic jam. Every new satellite we launch, every piece of an old rocket, even tiny fragments from collisions in the past, they all add to this congestion, making it an incredibly dangerous place to be.
So, how on earth do you solve a problem that complex? Well, you build a Guardian. And that brings us right into Section 2, where we get to meet the autonomous solution designed to protect all of our assets up there in orbit.
And here it is, the Autonomous Space Debris Avoidance Engine. Now, what is it? It's a really smart software system that doesn't just watch the sky, it actually predicts the future. It can identify a potential collision before it happens, and this is the most important part, it automatically calculates the single most fuel-efficient way for a satellite to just get out of the way, all on its own.
Okay, so that's the what, but how does it actually work? For that, we got to pop the hood. In Section 3, we're going to check out the engine's anatomy and the cool tech stack that makes it all possible.
The whole system is really split into two key parts. On one side, you've got the back end, and this is absolutely the brains of the whole operation. It's the powerhouse, the thing doing all the heavy lifting, crunching numbers, pulling in data, and planning those escape routes. Then, on the other side, you have the front end. Think of this as the window. It's a visual dashboard that lets you see everything that's happening in 3D, turning all that complicated data into something we can actually watch and understand.
So here's how all the pieces of the puzzle fit together. The SGP4 algorithm? That's kind of like a crystal ball for space junk. It predicts where everything's going to be. Then you've got reinforcement learning. That's the AI pilot, the smarts that learn the absolute best way to dodge. Fast API provides the speedy, powerful framework for the back end, while Cesium.js gives us that awesome 3D view. And then, wrapping it all up in a neat little package is Docker, which makes the whole thing super easy to set up and run just about anywhere.
So we have all the components, but how do they actually work together when the pressure's on? Well, Section 4 covers the collision avoidance playbook, breaking down that whole process from data to a final decision in just 4 critical steps.
It all starts by ingesting data. It pulls in something called two-line elements, or TLEs, which are basically the tracking info for everything floating around in orbit. Then, it uses that SGP4 algorithm we mentioned to predict where everything is headed. Step 3 is where it gets really serious. It identifies a conjunction, which is just the technical term for a dangerously close call. And finally, as soon as a threat is confirmed, the AI kicks in to plan the perfect, fuel-saving escape maneuver. From raw data to a life-saving decision in just 4 steps.
Now here's what's so cool about this. It isn't just a concept on a slide. Nope. This is a real software project that anyone with the right skills can actually run. So for all you developers watching right now, this next part is for you. First off, just a quick note on the setup. The project recommends using Python 3.12 or 3.13. That's going to give you the smoothest experience. If you use newer versions, you might just have to install a couple of extra tools. For any Python developers who want to get the back end running locally, the process is super straightforward. It's the standard playbook. Create a virtual environment, activate it, install the dependencies, and then run the server. These are all familiar commands that'll get the engine's brains up and running right on your own machine. But if you want to make things even simpler, the project is containerized. With Docker, you can get the entire backend running with just a single command. That's it. It makes getting started incredibly easy.
And once it's running,
this is how you interact with the engine, through these API endpoints. And if you look closely, you'll probably notice that they map directly to that 4-step playbook we just talked about. Ingest the data, propagate the paths, find the conjunctions, and plan the maneuver. These are the digital levers you pull to control the entire process.
So, for our last section, let's zoom all the way out and look at the bigger picture. What does an innovation like this really mean for the future of how we operate in space?
I think this quote from the project's own documentation is just incredibly telling. It says, "The system is built as a scaffold, a strong, predictable foundation. And the AI planner, it's pluggable." What that means is this isn't just some finished tool. It's a launch pad. It was designed from day one to be tested, to be expanded, and to be improved on by a whole community. That's just smart, practical engineering right there.
And that really brings us to our final thought. This project proves that elegant open-source code can serve as a guardian for our vital highways in space. And it leaves us with a pretty powerful question. If we can use this kind of accessible, intelligent technology to solve a problem like that, what other complex global challenges are just waiting for their own elegant solution? Thanks for joining this explainer.